So let us start the final session of our conference. First speaker is Professor Dmitri Sorokin from Padua. Please, Dima.
Thank you very much. It's very nice to be again at Lebedev Institute, though virtually. And thank you very much for the invitation. And today I'd like to present work which we have done in collaboration with Igor Bandas, Kurt Lechner, and Paul Townsend. And the main goal of this talk to present a new theory of nonlinear electrodynamics, which we call ModMax. So this theory is it turns out to be a unique nonlinear modification of free Maxwell theory that preserves all its symmetry properties. It of course presents Lorentz invariance and gauge symmetry, but in addition it also preserves electromagnetic duality and conformal invariance. And as we know, the dualities and conformal invariance play an important role in various lines of theoretical physics, ranging from condensed matter and up to the theory of fundamental interactions, and in particular in string theory. So I hope that this new theory fits into the title of this conference and may have applications within the lines of this title as well. So in general, as I learned myself recently, the different models of nonlinear electrodynamics have been studied quite extensively as possible guides for finding or describing new physics. In particular, there were models of nonlinear electrodynamics which address cosmological problems such as inflation and dark matter. And on the other side, these models are used for the effective description of properties of some insulator materials and the optical media. As most known examples, let me just mention the Born-Infield electrodynamics, which was proposed to solve the problem of finiteness of self-energy of charged particles, and which turned out to be very important part of string theory. And another example is the Euler-Heisenberg effective theory of quantum electrodynamics, basically an effective description of one-loop contributions, or fermionic contributions in electrodynamics, which was proposed in 1936. And there are many other models of nonlinear electrodynamics which have been proposed for different purposes. And the point is that the most of them has been constructed in a somewhat heuristic way and aimed to address and solve specific problems. And their construction don't use basic principle of theoretical physics such as fundamental symmetries, for example. Though I should note that, for example, conformal nonlinear electrodynamics have been quite extensively studied since 2000 at least, and I address you to this quite recent review on this subject. So the natural question was to ask what happens if we require both symmetries to be the theory of nonlinear electrodynamics, conformal invariance and duality invariance. It's somewhat surprising that this question has not been asked until recently, and the main goal of this talk is to answer this question. So let me start with a brief review of well-known facts about the invariances of Maxwell theory, just to set the notation. So the Maxwell action has the well-known form, which we can either write down explicitly in Lorentz invariant way using the gauge field strength answer, or in terms of electric and magnetic fields, which are components of this tensor. And the equations of motion of which one get from this action are well-known Maxwell equations. These are d mu of f mu nu equals 0, and they are accompanied by Bianchi identities. Or in terms of the electric and magnetic fields, we can rewrite them in this form. It's quite easy to see that the action and the equations of motion of this theory are conformally invariant. Well, maybe the full conformal invariance is not so obvious, but at least if you look at the scaling invariance of the theory, this is quite obvious. So if we rescale the coordinates with some parameter a in the way which I present here, and the gauge field with the inverse power of a, then we see that the Lagrangian and also equations of motion are scale invariant, and as a consequence, they are invariant under the full conformal group. The equations of motion of this theory are also invariant under duality rotations, which form the SO2 rotation group. That means that if we rotate the field strength and its dual by this SO2 matrix, we'll get the linear combination of these fields, and the corresponding equations of motion will have the same form. This symmetry in this formulation is only symmetry of equations of motion, but one can lift it to the level of the action that this is a different story. Now, if we will have a look at, let's now have a look at the generic nonlinear electrodynamics. So the action of this theory has the following form. The Lagrangian depends on two independent Lorentz invariants, which are constructed, which are f mu nu, and f mu nu dual. And these are, in 4 dimensions, these are only two independent Lorentz invariants, and there are no others. So one can construct the most general Lagrangian for nonlinear electrodynamics using these invariants. Here we will not consider these theories which have derivatives of these quantities, because they may lead to kind of Starogrodsky-like ghosts due to higher derivatives. So in general, this theory, of course, will not have neither electric magnetic duality, neither conformal invariance. But one can immediately find, for example, if one wants to have conformal invariance, then one can find the form of the Lagrangian easily. So it's enough to require that under this rescaling of these Lorentz invariants, for example, if we multiply f squared by a and f theta by a, then the Lagrangian should be the homogeneous function of degree 1, that is equivalent to a times L. And then this factor can be compensated by the corresponding rescaling of the integration measure. And the theory is at least scale invariant, but as a consequence, it will be fully conformal invariant. Alternatively, one can rewrite this same Lagrangian in this form, where the quadratic factor is just the Maxwell Lagrangian times some function, which is the ratio of these two invariants. Now, let's have a look at the equations of motion and to see what conditions on the Lagrangian are imposed by the duality, the requirement of duality invariance. So now the equations of motion have this form, where instead of f mu nu, we have the derivative of the Lagrangian with respect to f mu nu here. And then there are, of course, again, Bianchi identities. And what we want to have is that if we rotate these equations of motion by the SO2 matrix, then we'll get new equations in which we have some new Bianchi identities, and it is important that the equations of motion are the derivatives of the same Lagrangian functions with respect to new rotated variables as the initial Lagrangian. Then, as was first shown by Gaillard-Zumina and then elaborated by many other authors, including Gibbons and Rashid, one can find that this imposes the following condition on the derivatives on the Lagrangian function of this form. So if this condition is satisfied, then nonlinear electrodynamics is duality invariant. Again, the well-known example is Born-Infeld theory, which is basically the square root of the determinant of the Minkowski metric plus the field strength of the electromagnetic field, or you can write it down explicitly in this way. The square root is the function of f squared and f to the fourth term, where t is the dimension for coupling constant of the dimension of energy density, or it is also characterized as the tension of the D3 brane. And at the limit, when t goes to infinity, or equivalently when the field, electromagnetic field is weak, then this model reduces to Maxwell theory. But this theory is not conformally invariant. And so now, if we impose also the conformal invariance, in addition to this duality invariance condition on the nonlinear electrodynamics, so what we get? This is the theory which we called ModMax theory. Excuse me, do you hear me? Just this is a test that.
Yeah, we hear.
Okay, okay, very good. Thank you. So, as I said, this is a unique theory which has these properties and which reduces to Maxwell electrodynamics in the zero coupling limit. And its Lagrangian has this form. So it starts with the Maxwell like Lagrangian plus the square root of the fourth powers of this, or second powers of this f squared and fft the squared invariance. And equivalently, you can write it down in terms of electric and magnetic field. And here, cosine, hyperbolic cosine gamma and hyperbolic sine gamma is characterized the coupling constant in this theory, which is gamma, and this gamma is dimensionless. And when it is equal to 0, you can immediately see that the model reduces to Maxwell theory. A priori, the gamma can have positive or negative values, but as we'll see, there are physical restrictions which impose the condition that this gamma should be non-negative. Let's now have a look at the ModMax energy momentum tensor. Because of you see that it has very nice form. It is proportional to the Maxwell energy momentum tensor, and times some non-analytic function, non-analytic scalar function of Lorentz invariance. Its trace is 0 because of the conformal invariance and because it is proportional to the Maxwell tensor, of course. And one can also check that the energy tensor, which is the 0 component of this tensor, is always non-negative. Now you see that there is this non-analyticity here, and so this is a subtle point of the theory because it's non-analytic at the points where f squared and f of tilde are both equal to 0. And but we'll see how we can tackle this problem now. So this is problem is solved in the Hamiltonian formulation of the theory. So let me again write down the energy density which we got from the Lagrangian, you see that it has the following form, and the reason this energy density is not well defined at the points where E squared minus B squared equals 0 and E and B are orthogonal to each other. But these are physically very interesting configurations. These conditions on electric and magnetic fields are satisfied by electromagnetic plane waves, as we well know. So the question is whether these plane waves exist in this new theory, and it turns out that they do exist, but we can resolve this singularity by going to the Hamiltonian formulation of ModMax theory. To this end, we should perform the Legendre transform, so the usual Legendre transform. So we would like to find the Hamiltonian, basically the Hamiltonian form of the same energy density T00 by performing the Legendre transform and introducing the vector D, which is canonical conjugate moment of the electric field E here. That is, D is defined as the variation of the Lagrangian with respect to the electric field. Conversely, using the Legendre transform, we can invert this relation and express E as the function of D and B, which is the derivative of the Hamiltonian. And the Legendre transform can be explicitly done in this theory, and the Hamiltonian has the following form. So you may compare the Hamiltonian with the Lagrangian density. Let me just quickly flash again the Lagrangian, and the Hamiltonian in this theory has this form. The difference is in the sign of hyperbolic sign of gamma here. But what you can immediately see that the Hamiltonian, which is equivalent to the energy density T00, don't have any singularity at the points where E squared minus B squared and E times B equals 0. Moreover, in the Hamiltonian formulation, what we see immediately is that this theory is manifestly duality invariant under the rotations of the vector D and B here. Okay, so I was telling about the plane waves, and so let's see now how do they look like in this theory. To this end, we should.
May I interrupt you?
Yes, please.
Can you go back to the Lagrangian, please?
Yes.
Yeah. Yeah, there was this denominator. No, there's one next, I think. Okay, this is fine. I just wanted to mention that this seeming singularity is probably a fake, even at the Lagrangian level, because the numerator is always smaller than denominator, so it's bounded by 1. This factor.
Yes.
So it can never develop a singularity, actually.
You are right, Misha. This is not a singularity in the sense of infinity. This is uncertainty that this f squared divided by the square root can take values from -1 to 1.
Okay, thank you.
In this sense, yes.
Yeah, thanks.
You are right. 0 by 0 is not more than 1, the modulus of this, yes. Okay, so let me now show the equations of motion in the Hamiltonian formulation. They are also, I hope, well known. Now you see that E and H appear here as functions defined as derivatives of the Hamiltonian with respect to the vector D, and H is with respect to B, which are called constituent relations. And quite surprisingly, also for us, it turned out that these equations have the exact plane wave solutions. That means that as I told before, E squared minus B squared is 0 and E times B equals 0, but it does not mean that D squared minus B squared equals 0 and DB equals 0 here. The only relation which is imposed by these two conditions on the quantities D and B is this one. And it turns out that the plane wave solutions only exist for gamma equal or greater to 0. And the Hamiltonian for these plane wave solutions, as in the Maxwell theory, it's becomes the module of the momentum density, electromagnetic momentum density, which is D by B here. And the solution in terms of D and B has the standard form for the plane wave solutions, so that they can be written as the complex vector D plus IB, which has this structure with D0 and B0 being constant complex amplitude and K being the momentum of the plane wave. As a similar example, one can show that the solution in which D and B are orthogonal is very simple. Then the electric field is proportional to the electric displacement vector in this with the parameter e to the minus gamma, and has the following cosine structure. So this is the standard plane wave solution here. Let me now discuss a different interesting property of almost all nonlinear electrodynamics, including ModMax. It is called Birefringence. This is the property of the propagation of light in uniform constant electric or magnetic backgrounds. It turns out that in nonlinear electrodynamics, in these uniform backgrounds, the ray of light splits into two parts due to its polarization with respect to the background. And these two rays of light take different paths characterized by different dispersion relations. So the general structure of dispersion relations is of this form, where lambda plus and lambda minus are two different functions of the momentum of the wave, and it depends on the properties of the background. And these functions are determined by the structure of nonlinear electrodynamics. Here, in the case of ModMax, this Birefringence phenomenon is quite peculiar. So one of the modes propagates with the standard along the standard light cone with the speed of light, while the second one propagates with the following dispersion relation, where phi here is the angle between the direction of the propagation of the ray and the direction of the external magnetic field. So in the case of ModMax, due to basically conformal invariance, there is no dependence on the strength of the magnetic field in this phenomenon. And one can see that from this expression that if gamma were negative, then these propagating modes might be superluminal, thus violating causality. And this again singles out the non-negative values of parameter gamma here. Let me just show now the properties of Birefringence or other theories. So there is a parameter or index called the Birefringence index, delta m, which is the difference between lambda plus and minus lambda minus here, so that when it is 0, then there is no Birefringence. And this is the case for the Maxwell theory, of course, because it's non-interacting, but it also the case for the Born-Infeld theory. So the Born-Infeld is almost unique nonlinear electrodynamics, which does not have this property. On the contrast, in the quantum electrodynamics, the effect is present, and it is the quantum computation shows that it should be of this magnitude, where B is the magnitude of external electromagnetic field. And in the case of the ModMax, you see that if when the angle between the ray and the external field is 9 degrees, then this birefringence effect is maximum and has this property here. There were some recent experiments conducted actually here near Padua in Lignara. They are called PVLAS experiment, polarization of vacuum with lasers, where they tried to measure the birefringence, and they imposed bounds using their measurements. So the bounds on this index is of this value for very big electromagnetic field. And using this bound, one may estimate the value, experimental value of the parameter gamma in ModMax theory, in principle. Okay.
But yes. This estimate purely classical, just estimate.
Yes, this is in ModMax. This estimation is purely classical. Good. Also for the Born field, it's purely classical, of course.
But yes, but
when you consider it as just the nonlinear theory, which does not have any quantum contributions of any other particles. Yes, of course. Okay, how much time do I have, actually?
You have just 4 minutes until official.
Okay, 4 minutes, I think I will almost...
You can take a few minutes from next question.
Okay, let me now just briefly sketch some applications in the study of effects of this ModMax theory on black holes. There have been several papers which appeared, which studied the ModMax effects on some compact self-gravitating objects. And what we would like to consider is the coupling of the ModMax to gravity, or Einstein gravity. And as an example, let's consider an electrically charged Rising-Nordstrom black hole. So it has the standard metric of this form, where Fr is the parameter which depends on the radial coordinate of the black hole, and the parameter m and q squared are respectively the mass and the charge of the black hole. And here you see the effect of ModMax. It normalizes the electric charge of this black hole, this coefficient. And as always, for the Rising-Nordstrom black holes, there are 2 horizons, and there is an extremal situation when m squared equals to q squared, then we have the unique horizon. And in this theory, there is a kind of screening effect, so that mass actually can be less than the actual electric charge of the black hole if gamma is positive. So this is an effect of the nonlinearity of ModMax on the extremality condition for the Rising-Nordstrom black hole. Well, let me, in the remaining 2 minutes, just flash the generalizations of this theory. It can be actually generalized to Born-Infield-like theory. So the Lagrangian of this generalized theory has this form here. So it reduces to the Born-Infield Lagrangian when gamma is equal to 0, as you can see. And when the tension is going to infinity, then this generalized Born-Infield theory reduces instead to ModMax theory. Of course, this generalized theory does not have conformal invariance, but it is still duality invariant. And another example of the generalization, let me just present a 6-dimensional conformal interacting chiral two-form theory. In the PST formalism, the action has this form, where now we are dealing with a two-form gauge field AMN. Its 3-form field strength is H, V here is the derivative of the scalar auxiliary scalar field, which can be eliminated by gauge fixing on the price of losing the manifest Lorentz invariance. H theta is defined in this way, and the vector omega m is as follows. So this is the action for this theory. And again, if we put gamma equals to 0, then it reduces to the non-interacting, well-known chiral two-form theory in 6 dimensions. And if you perform the dimensional reduction to 4 dimensions, it reduces again to ModMax theory. So I have reached my conclusions, and so let me briefly flash what we have talked about. So the ModMax theory is a unique nonlinear extension of Maxwell theory, which preserves all its symmetries, and there is a 6-dimensional unique theory of conformal interacting chiral two-form, which reduces to ModMax upon dimensional reduction. This theory has a dimensionless parameter, which should be non-negative. There are plane wave solutions, but generically there is no superposition principle because of the non-linearity. And it turns out that recently in this paper, Desi and Gavier found topologically non-trivial Hopfield knot solutions in this theory, which is quite interesting as well. Then the ModMax has this effect of Birefringence, which may be used to test experimentally this theory. As further developments, one can consider detailed study of properties of this theory in the presence of charged sources, electric and magnetic one. Then one may ask what if this theory can be quantized in one way or another. Then one can proceed with studying effects of this theory in gravity and modified gravity theories for applications in black hole physics and cosmology. And then I think there might be very interesting applications in condensed matter and optic physics, in particular using gravity condensed matter holography technique for describing effective properties of materials in this in condensed matter physics. The natural question has been whether this theory can be supersymmetrized, and it turns out that it is, and we have done this with Igor, Kurt, and Paul, and independently Sergei Kuzenko also did this, and the papers are about to be released very soon. So thank you very much.
Thank you very much, Dima, for very nice talk. So now we have time for maybe for two questions, please. Arkady, yes.
Arkady, go.
I have a comment. So in Born-Infeld action, the point-like charge, electric charge, has finite energy and it's non-singular solution. So here, it's basically the same solution as in Maxwell theory, which is usually one of our potential, just with a rescaled charge.
Right, yes.
So yeah, there's a big quantitative difference. So there's no regularity, which was in Born-Infeld.
Yeah,
it's a feature of this theory, which is related to the absence of mass scale. So in Born-Infeld, you have a scale. Here you don't, because you have this conformal invariance.
Yeah, right. Yes.
But the second question is, so the main issue, well, the main feature is lack of, it's non-analytic in fields, right? So you have a root. So for example, the question about gluon amplitudes here, which is meaningful in Born-Infeld action, here is not meaningful. You can't expand near trivial vacuum. So,
well, I think you can do it in the Hamiltonian formulation.
Well, I don't know.
As I tried to show, sorry?
No, No, in Hamiltonian it's still not a square root. You have a square root.
Yeah, but the square root is there is a subtlety, but in the Hamiltonian form we believe that we cannot reach the values of d squared and b squared such that the square root becomes 0. That's
but my question is not about zero, non-zero, or singularity. It's just a question of expanding near small f. It's a small f menu.
Okay. Yes. Sorry. Yes.
So, what we need really, as you discussed in this birefringence story, you need a background field, constant or PP, or some plane wave background on which you expand. Then you have scattering on this background, but then you break conformal invariance.
Yes.
It's just a feature of this theory.
Yeah, this is the feature of this theory. And actually it is the feature of any conformal nonlinear electrodynamics. They are all of this kind, I think.
Yeah, and finally, one could hope that conformal invariance somehow helps the quantum level, but I don't think that is true because, for example, Born-Infield action by itself is not well defined at the quantum level. So same here, you don't, essentially.
Yeah, here I think it's very interesting question because formally there is no dimensionful parameters in theory.
Yeah, but it's
but of course it's non-analytic.
At the quantum level, that's not. It's just like it depends on which. What do we mean by what we're looking for? If you start computing divergences, I'm pretty sure you'll get divergences which will not preserve the symmetry.
I propose to continue this discussion between Arkady and Dima to this discussion, or general discussion. So I have now we have room only for one short question. Misha Vasilyev. Okay. Sergei Kuzenko, you here? Are you here?
So I'm not quite sure, Zhenya, why did not what about me?
Yeah, you here. Yes, I lost you for some reason.
I see. I have very, very short question. Just, I mean, are there any restrictions on the gamma parameter from any experimental data?
This is what I was trying to show. This Birefringence experiment may restrict. Sorry, Misha.
I mean, this is the only one you say.
Yes, the only one which I know, but in principle, probably one should have try to find another one. So we have just started to work on this, and this is the only one which I can propose at the moment.
Okay.
Okay, so I propose to stop discussion and